సార్ సార్ స్పీకర్ ఆన్ చేయండి. మీ స్పీకర్ ఆన్ చేసుకోండి సార్. ఆన్లైన్ క్లాసెస్ లాగిన్స్ చేస్తున్నారు కదా, స్పీకర్ ఆఫ్ ఉంది.
ఇప్పుడు
ఓకే సార్. స్కెచ్ బుక్ ఓపెన్ చేసుకోండి.
చేశా నేను.
షేర్ స్క్రీన్ కొట్టుకోండి.
ఎక్కడ స్కెచ్ బుక్ లో విండో దగ్గరికి వెళ్ళాలా? షేర్ స్క్రీన్
ఇక్కడే ఉంటుంది సార్. షేర్ స్క్రీన్
ఎక్కడ? స్కెచ్ బుక్ లో షేర్ స్క్రీన్ ఉందా? లేదు లేదు, దీంట్లో ఉంటుంది షేర్ స్క్రీన్. హలో
సార్.
నాన్న
అందులోనే ఉంటుంది సార్ షేర్ స్క్రీన్.
రీనేమ్, మేక్ హోస్ట్, రిమూవ్. ఎక్కడ ఉంది షేర్ స్క్రీన్?
పైన మీకు గ్రీన్ కలర్ లో కనిపిస్తుందా?
గ్రీన్ కలర్ కనిపించింది.
ఒక్కసారి
షేర్ స్క్రీన్ కొట్టా.
షేర్ స్క్రీన్ లో అడ్వాన్స్డ్ పోర్షన్ ఆఫ్ ది స్క్రీన్ లో
ఢిల్లీ నుంచి వేసినట్టు గుర్తు నాకు.
అడ్వాన్స్డ్ కొట్టా.
పోర్షన్ ఆఫ్ ది స్క్రీన్.
ఇంకెక్కడ పోర్షన్? ఇది ఇందులో ఏం లేదే.
ఓపెన్ అయిందా? షేర్ స్క్రీన్ లో మీకు విండోస్ ఓపెన్ అయిందా?
షేర్ స్క్రీన్ కొట్టాను.
ఉంటుంది చూడండి క్లియర్.
ఇప్పుడు జూమ్ వెబినార్ అని ఉంది కదా, దాంట్లో నా ఫేస్ వచ్చింది. ఏం చేయాలి? ఆడ గ్రీన్ కలర్ టిక్ ఉంది, అది కొడితే షేర్ స్క్రీన్ వచ్చింది.
అవును, షేర్ స్క్రీన్ కొట్టారు కదా.
షేర్ స్క్రీన్ కొట్టా.
ఏమొచ్చింది?
షేర్ స్క్రీన్ వచ్చింది. కింద ఏదో అడ్వాన్స్ ఉంది.
అడ్వాన్స్ క్లిక్ చేయండి.
క్లిక్ చేశా. స్క్రీన్ క్యాప్చర్ మోడ్ ఆటో అని వచ్చింది.
నిన్న చూపించాను కదా సార్ క్లియర్.
అచ్చా, మీ ఆ జూమ్ కి వెళ్ళనా? అయితే
జూమ్ కి కాదు సార్, ఉండండి, నేను నార్మల్ కాల్ చేస్తాను.
హలో, స్పీకరా? నా హెడ్ స్పీకరా? ఆఫ్ చేశా. హలో, హలో.
సార్ చాట్ చేసుకోండి.
ఇదేంటి అందరూ రైజ్ హ్యాండ్ అని వస్తుంది?
నేను క్లోజ్ చేశాను సార్, మీరు స్టార్ట్ చేయండి.
వాయిస్ వినబడుతుందా అన్న?
ఎస్, పర్ఫెక్ట్ గా ఉంది సార్, మీరు స్టార్ట్ చేసుకోండి.
మరి నా ఫేస్ కనపడుతుందా?
యా, ఎవ్రీథింగ్ ఇస్ ఫైన్ సార్, యూ కెన్ స్టార్ట్.
ఓకే దెన్, థ్యాంక్ యూ. Okay, good evening everyone. I am Kiran Kumar. I teach analog circuits at ACE Academy. I have joined this institute in 2006, right? So let's get started. Let's go through the syllabus first. First, we'll look at introduction. In introduction, we'll introduce basic Ohm's law, only the application part, KVL, KCL, simple filters, and dependent sources. Ohm's law, KVL, KCL, simple filters, and dependent sources, right? Then we'll take op-amp as a basic abstraction, as a basic black box. And here we look at open loop configuration, negative feedback, and positive feedback circuits. We introduce diode applications, diode. Here we discuss rectifier, peak detector, clipper, clampers. And then we'll introduce BJT and MOSFET simultaneously, right? So once we finish BJT DC analysis, we take over MOSFET DC also.
సార్
స్క్రీన్ ఎక్కడ కనపడలేదు,
మళ్ళా పోయినట్టుంది, మీరు చూడండి. మళ్ళీ షేర్ స్క్రీన్ కొట్టండి.
ఎక్కడ గూగుల్ క్రోమ్ నుంచి రావాలా మళ్ళా?
లేదు లేదు, ఇందులోనే జూమ్ లోనే. ఇప్పుడు మన దాంట్లోనే ఇందాకే కొట్టినట్టే మళ్ళా కొట్టండి సార్.
ఇప్పుడు మొత్తం పోయిందిగా.
మళ్ళా షేర్ స్క్రీన్ కొట్టండి. సార్ ఇందాక చూపించినట్టే సేమ్ అదే ఫార్మాట్ లో మళ్ళీ వెళ్ళండి సార్.
All formats of the questions you can have about multiple choice, you can have about numerical answer type.
రెండు స్టార్టింగ్.
So that's why this post.
హలో. ఏది ఇప్పుడు ఫస్ట్ హలో. ఓకే. Fine. Let's get started. Some problem, right? Yeah. First, we look at introduction, then op-amp as a basic abstraction, a black box. Then we'll see diode applications and BJT and MOSFET both simultaneously. For example, BJT and MOSFET, if you look at DC analysis and AC analysis. In DC analysis, we will learn to calculate DC currents and voltages, right? So here, biasing is one topic, and then current mirrors. These are used to bias differential structures. For AC analysis, we will learn to calculate AV, AI, AP. AV stands for voltage gain. I'll mention this again. AP is power gain, Rin, input resistance, R0, tau, and bandwidth. So these are the things we try to calculate. But here we will look at configurations, right? So if there is a common emitter, what are the three configurations? Common emitter, common base, common collector. So here, this is common source, common gate, and common drain, right? And then we will combine them. We will try to cascade common emitter with common base. This is a cascade structure. Common source, common gate, right? And then other configurations like common collector with common emitter. And regarding your doubts, I'll give you time in the end, right? So we will have ample amount of time at the end. Then you can ask whatever the doubts you get as on when. Please jot down on a piece of paper, and then I'll come back, right? Then we have a common collector with common emitter. Which is common drain with common source. So these are the different wideband amplifiers which combat Miller effect. And then once we finish BJT and MOSFET, then we can go for Zener circuits. Then we have Zener circuits, oscillators, and op-amp non-idealities. Non-idealities of op-amp would include all the offset problems, slew rate, CMRR, and so on, right? So this will end the syllabus. So I repeat, first we'll start with introduction, Ohm's law, KVL, KCL, simple filters, dependent sources, op-amp, 3 modes of operation, open loop, negative feedback, positive feedback. So I might introduce diode in between so that we can combine op-amp with diode and start doing rectifiers and precision rectifiers, peak detector, precision peak detector, clipper, clampers, BJT and MOSFET. In BJT and MOSFET, we'll do it simultaneously, right? So if I do DC analysis in BJT and then we go for MOSFET simultaneously, current mirrors, right? Configurations. And here we have differential structures also. Differential structures. Zener circuits, oscillators, and feedback amplifier. Some of the students, they have a doubt, what about feedback amplifiers, positive feedback, negative feedback, so on and so forth. But my opinion is, if there is an oscillator, there is an amplifier, and there's a Schmitt trigger, then it's understood that you have both negative feedback structures as well as positive feedback in the syllabus, right? And Zener, the reason why I've introduced Zener here is Zener is there in EDC. So we cannot complain if some voltage regulator, a simple Zener problem is given. Though Zener is not mentioned in the syllabus, so we will look at basic Zener circuits there. So we look at feedback amplifiers, Zener circuits, oscillators, however, sinusoidal and non-sinusoidal. And at the end, we'll look at op-amp non-idealities, right? Power amplifier, some IES students are there, so I might, but timers is not included in the syllabus, right? If you want, we can do it, but we'll see, right? So this is about the syllabus. So we'll get going now. Yeah, one more thing. I'll give you a simple circuit, and I'll give you a circuit, and let's see if you can identify the syllabus. So this is just for fun. I'll give you a simple circuit, and let's see if you can identify the elements so that the whole syllabus is there in that circuit, right? So what if I draw something like this? I have to get used to. Not able to draw. Can you identify the syllabus in this circuit? Now, please, this is just for fun, right? It's just for fun, right? So it doesn't matter. So what do you see in this circuit? So can you identify the whole syllabus in this? If you look at the basic configurations, what are the three configurations? We have common emitter, common base, and common collector, right? So wherever emitter is grounded, so you can call, whenever emitter is grounded, you can call it a common emitter model, common emitter structure. And we'll spend at least half an hour on this basic structure, right? So we'll try to calculate the input resistance, output resistance, gain, and that is expected from a student, right? You take a simple common emitter, spend a lot of time. So once we finish common emitter, we might go to common base, SCB, a common base structure, right? So once we finish common emitter, common base, this is common collector. Input is base, output at collector, this is common collector. It's just an identity, it's just for fun, right? The common emitter, common base, common collector. So if you combine these two, you might get a cascode, right? And the combination here is a current mirror. This is another topic again. So we'll spend around 2-3 hours just on this topic, current mirror. A common collector with common base. If you combine, again, there's another topic called the differential structure. And the second stage is the gain stage. So this is a Darlington pair, gain stage. So we'll spend a lot of time on calculating the input resistance. The third one is a basic level shifter. And this is a common collector configuration. So this is a power amplifier. So now you know what I'm drawing. It's just for fun, don't worry. The whole combination is our first topic, which is a op-amp. Now students, they have so much fun looking at this black box because we are neglecting all the linear stuff inside and we are interested only in the terminal behavior. What happens at the plus terminal, what happens at the minus terminal, right? So what are these arrows here? The arrows here, the arrows here. These arrows here are nothing but the supply limits, right? So this is I mean, just for fun, don't worry. So at the end of this course, what is expected from a student? A student should be able to calculate Rn, R0, AV, AI, AP, tau, bandwidth, all the parameters of amplifier just by inspection. So without doing even the small signal model, just by looking at the circuit, you should be able to contemplate all these different parameters just by inspection. By looking at the common emitter, you have to say, you know, at the base terminal you have R pi, the emitter terminal it's alpha by GM, at collector it's R0. So something like that, right? So we'll do it as on when time comes. I'll see that you practice in that fashion, and then you can play around. Once a bigger circuit is given, you can start playing around, right? Okay. Yeah. So we'll start with the introduction now. Okay. So first is Ohm's law. Ohm's law. Find VB and I. Find VB and IB. A battery is given, 4.25 volt, and a light bulb is given. Light bulb, and the characteristics of the bulb is also given. Two volt, 0.02, 4 volt, 0.04. So these are characteristics, VB and IB. There's 2 volt, there's 0.02, there's 4 volt, 0.04, 5 volt, 0.05. Right? So you're supposed to find VB and IB. So this is the first question. You can just go through simple problem. Yeah. Now one method is by graphical approach, which we don't do in analog, right? The graphical approach is by looking at this table or looking at the graph here, you can choose an operating point. For example, if the supply voltage is 2 volt, then the current is 0.02. If it is 4 volt, it's 0.04. If it's 5 volt, it's 0.05. So you can expect for 4.25 volt, what is the current? It should be 0.0425, is it not? Instead, what is the method in analog? Because in analog, what is the first step in analog is, we will look at the characteristics of the device. It could be a diode or a BJT. And from there, we will find an equivalent model for that device, right? This is the first step in analog. Somebody gives you a diode, right? What happens inside the diode, we are not bothered, right? We are interested only in the terminal behavior. So the first step in analog is characteristics. From the characteristics, if you can have a simple model of a diode, like a on switch or an off switch, then you can start analyzing circuits very easily, right? So that's the intention. Now, a bulb is a very simple example, very, very simple example. It has a linear relationship with the current and the voltage, right? Now, if a line passes through the origin, whenever a line passes through the origin, what is the equation? The equation is y equal to mx. Am I right? Y equal to mx. On y-axis, you have current IB. On x-axis, you have voltage VB. So what is VB by IB? It is 1 by m, 1 by slope. What is slope here? Change of y by change of x. So it is 2 by 0.02, which is 100 ohms. Why am I saying ohms? Because the ratio between voltage and current is resistance, right? So it should be 100 ohms, that's the units. Now, we will replace a bulb with an equivalent element now. This is called its model. So what is the first step in engineering? First step in analog is we model systems. So whenever a bulb is given, next time you find a bulb in the lab, so you can start imagining that it is what? A resistor. Or if you don't find if you don't find a resistor in the lab and you want to limit the flow of current, then what you'll do, and you have a bulb around you, then you can always put a bulb in the place of a resistor, because the bulb is now behaving its character. The bulb character is now a resistor of 100 ohms, right? So let us replace the voltage, let us replace the bulb with a resistor. So now you go around and see what are the resistors in your house. So I keep, my son is in 7th standard. So there's electricity introduced to him, and there in the syllabus, there is no Ohm's law. There's just resistor, current, and voltage. So I was asking him, what are the resistors that you find around which limits the flow of current, right? So the heater in your house can be imagined to be a resistor. The bulb, the television set can be modeled as a single element called resistor. Whenever there is a current, as voltage increases, the current also increases. So the simple example is a bulb or a heater in your house. So similarly, when we look at complicated structures like the BJT and MOSFET, you can start imagining, how can I model them with simple resistors and dependent sources? We can try to model. You can have some large signal and small signal models like that, right? So what is a bulb now finally? A bulb is a 100 ohm resistor. Now you tell me, what is the relationship between V, I, and R? This is Ohm's law. We know that V equal to Ri. Am I right? So what is IB? It is 4.25 by 100. This is the answer, 0.0425. Am I right? So now you tell me, on the characteristics, what is the operating point that you have chosen? This is the characteristics. You have given 4.25 volt, and this is 0.0. So for 4 volt, it was not 4. For 4.25, it's 0.0425, right? So this, any name you want, is that point a stable point or is it moving? It is definitely a stable point. It's a fixed point, right? So any fixed point or a static point can also be called as a Q point or a quiescent point. So you can call it a Q point. So what is a Q point now? If I give 4.25 volt, this is the current that I get. If I give 5 volt, I'm getting 0.05. If I give 6 volt, I'm getting 0.06. So this is the operating point you have chosen on the graph, right? So this is simple Ohm's law. And note, so next time you have a resistor, what happens if there are two voltages, V1 and V2, there's an R here. What is the current I? This is very, very important. I is nothing but, it's not V by R, it's now V1 minus V2 by R. Current always flows from a higher potential to lower potential. So similarly, if this is V2 and this is V1, I have an I. What is I? It's V2 minus V1 by R. All right? Yep. Okay. So this is simple Ohm's law. I've given you a bulb. Now we know how to model a bulb or a heater in your house. You can replace that by a resistor, right? Similarly, what are the capacitors that you find in day-to-day life, right? Have you find capacitor, the flashlight in your digital camera? You can model it with a capacitor, right? Even the screen, that's a capacitive load, right? So there are so many capacitors in our day-to-day life, we can model them, right? Whenever you find such an element, you can replace it by an equivalent capacitance, right? Okay. Now, we'll go for a this is a gate problem. This is a gate problem, analog related to Ohm's law. So you can solve it. I'll give you 1 minute time, right? And then I'll solve. Find What is this? VB and IB if the characteristics oh my god, we'll take a fresh page. This line about find VB and IB if the characteristics of the device is given. Okay, so this is the problem. You can solve this. This is a gate problem. Give you 1 minute time, then we'll solve it. Okay. Yeah. Now, in the previous example, we had a line passing through the origin. So how do we characterize that straight line? That is y equal to mx, right? But now, how do we characterize this straight line? We have 2 points here, 0.6 volt, comma 0. And then there is 0.7 volt, comma 1 milli. So how do we characterize this straight line? This is x1, y1, x2, y2, right? So what is the equation of a line? A straight line? It's y minus y1 is y2 minus y1 by x2 minus x1 into x minus x1. On y-axis you have current, and what is y1? y1 is 0, y2 minus y1. y2 minus y1 is 1 milliampere minus 0 by 0.7 minus 0.6, which is x minus x1. X-axis you have voltage, and what is x1 here? x1 is 0.6. So what is VB? VB is equal to, so 0.1 by 1 milli, it's 100 IB plus 0.6 volt. Now, how do we model this, right? So VB is a voltage, 100 IB is the voltage, and 0.6 volt is the voltage, right? So voltage equal to voltage plus voltage. So we know we cannot add horses with donkeys, right? If this is voltage, this is also voltage. So how do we model it? You have a voltage VB. There's a resistor of 100 ohms, and then there's a voltage 0.6 volt. So this voltage is equal to 100 into IB plus 0.6. Now what do? This is the equivalent model. Equivalent model of whatever, right? The circuit that is given, of the device that is given, right? Now, this is 5 volt, 1K. We had a device here. That device is replaced by 100 ohms with 0.6 volt. And this is your VB, and you have a current I. Now, what is IB and VB now? You can apply KVL. KVL minus 5 plus IB into 1K plus 100 plus 0.6 equal to 0. So what is IB? It is V1 minus V2, 5 minus 0.6 by 1100, right? And what is VB? VB is going to be IB into 100 plus 0.6. So what is the operating point that you have chosen on the graph? This is a graph. On this graph, what is your VB and IB, right? This VB if I remember, it's around 1 volt. So if it's 1, this is 4 milliampere. So this is your Q point. Oh my God, how did this come? Okay, so this is the Q point. It's 1 volt. Okay. వెంకట్ ఈ స్క్రీన్ ఎట్లా తీయాలి? వస్తున్నా. సరే ఓపెన్ చేస్తా. ఇది మళ్ళా వచ్చింది. మళ్ళా వచ్చిందిగా. అది చేసినా ఇలానే వస్తుంది. ఫైల్ క్లోజ్ చేయాలా? ఇది విండో డిఫాల్ట్ పెడితే రావాలి కదా. Okay. Fine. Some problem. This is about Ohm's law. Now, what if we have bulbs in series, right? If you have bulbs in series, you know how to apply KVL, right? So you have resistors in series. V, R1, R2, R3. So KVL states that the algebraic sum of voltages in a loop is what? 0. So you can go clockwise or anti-clockwise, so it's not going to change. So I take the sign that comes first, right? So the sign that comes first is negative. Minus V plus V1 plus V2 plus V3 equal to 0, right? And one more very, very important thing is the voltage division rule. The voltage divider rule will always give you a fraction of the input voltage. For example, if you have a voltage V and two resistors R1 and R2, how do you find the voltage across R2? Say V2. The current I is V by R1 plus R2. And what is V2? It is I into R2, which is V by R1 plus R2 into R2. Now, why is this so important, right? It's so important because what if R2 is a short circuit, or what if R2 is an open circuit? So how will you deal with this? హలో, ఇది పోవట్లేదు. అది కొత్త ఫైల్ ఓపెన్ చేస్తే ఒక పేజే వస్తుంది. ఏంటి? క్లోజ్ చేస్తున్నా మొత్తం. ఈ చెక్స్ ఎందుకు వస్తున్నారా బాబు? Ekkadundi portion of the screen? Whiteboard kottana? ఇందులో చెప్పేసుకుంటా నేను. Okay. I'm sorry. I'm not used to all this. Yeah, I was trying to say that why the voltage division rule is so important. Say, for example, you have an open circuit condition. And the short circuit condition. Now, what if R2 is an open circuit? You have only R1. Or what if R2 is a short circuit? So it happens many a times when you're doing clippers and clampers problems, right? In the previous example, we have seen V2 equal to VR2 by R1 plus R2. Or it is V by 1 plus R1 by R2. Now here R2 is nothing but infinite ohms, infinite. In a short circuit condition, R2 is 0. Am I right? So what if R2 is infinite? Then V2 equal to V. So we understand that if there is an open circuit, then the whole voltage is going to get manifested. Whereas here, what is I here? I is V by R1 and V2 is VR2 by R1 plus R2. And if R2 is 0, V2 is 0. So what do we understand now? Well, now we come to a very important conclusion here. The conclusion is, if the current is 0, doesn't matter about the voltage. If the current is 0, then we can model systems with an open circuit. The current 0 means open circuit. If the voltage is 0, so you can model those systems with short circuit. For example, you have a capacitor. The current flowing through the capacitor is 0. Then you can replace the capacitor with an open circuit. If the voltage across the capacitor is 0, then you can model the capacitor with a short circuit. You can replace the capacitor and connect a short circuit and then do some circuit analysis. So whenever current is 0, you can model those systems with open circuit. Whenever voltage is 0, you can model such systems with short circuit. For example, a diode current is 0 in reverse bias. A diode current is 0 in reverse bias. Then how do we model such a diode? The diode is replaced with a open circuit, right? If the voltage across a diode is 0, if the voltage across a diode is 0 in forward bias, for example, if the voltage across a diode is 0, whenever voltage is 0, you can replace the device with a short circuit. It looks simple, but it is very, very important, right? Current 0, open circuit, voltage 0, short circuit. So if somebody says that in an open circuit you have maximum voltage, minimum voltage, don't believe them, right? You have to say that in an open circuit, don't talk about voltages, talk only about current. If somebody says that in a short circuit you have maximum current, minimum current, don't believe them, right? So whenever the voltage across a device is 0, then that device can be replaced with short circuit. But the current, it depends on what sort of elements that you connect in that loop, right? So don't talk about currents in a short circuit. Don't talk about voltages in a open circuit. So what is important in an open circuit is not voltage, it is current. What is important in a short circuit is voltage, but not current, right? So voltage 0, I repeat, a diode In forward bias, its voltage is 0. What is a diode? A diode behaves as if it is a short circuit. If the current flowing through the diode in reverse bias is 0, what is a diode? The diode can be replaced with open circuit. So it looks simple, but very, very important. So this comes with a simple idea, the voltage divider rule. Very, very powerful rule, right? So similarly, what about the current divider rule, right? So the current divider rule. Right? Now, when will you apply current division? On what occasion you can apply current division, right? So one simple idea is if two resistors are in parallel, then however you can apply, right? But if two resistors experience the same potential difference and the current is dividing, then also you can apply. For example, if two resistors are in parallel, R1, R2, I1 and I2, and the total current is I. Then the current entering is equal to the current leaving, I equal to I1 plus I2. So I forgot to tell you here, what is KCL? KCL, the currents that meet a node is equal to the currents that leave that node, right? The currents entering, suppose here you have I1, I2 and I3. And this is I4 and I5. So what is current division here? The currents that entering the node is equal to the currents that are leaving the node. I1 plus I2 plus I3 is I4 plus I5. Okay. Right? Fine. So I is I1 plus I2. And what is V? V is nothing but I1 R1. And the same V is I2 R2. Okay. Now if you solve them, what do you get? I1 is total current into the opposite arm. And what is I2? I2 is I into R1 by R1 plus R. Okay, so in the end, I'll give you the screenshot of all this. But if you want, you can always take a screenshot as on when it is required, right? But I would recommend a student writing along with me, right? Because writing something, you will remember it much better, right? Fine. Yeah. When can you apply current division? You can as well apply if two resistors experience the same potential difference. Now this also looks simple, but it's important because sometimes in when you're doing op-amp circuits, you have a Vx and Vy. So one might be some virtual ground, the other one is the common ground, some voltages, right? Vx, and if Vx and Vy both are same, suppose your Vy is Vx and this is R1 and R. This is I1 and I2. Now, what is the total current I? I is I1 plus I2. And the second equation is, suppose this node is Vz. What is Vz minus Vx? It is again I1 R1. It is again I2 R2. Right? So you can apply current division if two resistors experience the same potential difference. And of course, the current should divide. The current I, which is entering, should leave as I1 and I2. Now, just observe the two equations in the previous slide and this slide. in the previous slide, we have I equal to I1 plus I2. In the present slide, I is I1 plus I2. In the previous slide, I1 R1 equal to I2 R2. In the present slide, I1 R1 equal to I2 R2, right? So if you solve them, you get I1 equal to I into R2 by R1 plus R2. And I2 is I R1 by R1 plus R2. So now when can you apply current division? I mean, of course, the current should divide, but at the same time, when it is dividing into the two resistors, right, those two resistors should experience the same potential difference. For example, if I have a MOSFET here, or if I have an op amp or a BJT here, and so happens that this V is equal to this V, and you have R1 and R2, and the total current is I. Now you can apply, right? So you can apply, they have I1 here, you have I2 here. Then what is directly I1? I1 is I R2 by R1 plus R2. And what is I2? I R1 by R1 plus R2, just as an example, right? So you can always apply current division if two resistors experience the same potential difference, and the current should, however, divide, right? So one is the voltage division rule, the other one is the current divider rule. Very, very important. So these are simple tools, you need them. And can I replace the voltage divider? Can I replace the voltage divider with a single voltage source? Suppose this is AB, VAB, in series with a resistance. Can I do this? So this technique I might need when I'm doing the voltage divider bias circuit, right? So you have a voltage divider or any sort of a linear mesh which has many resistors and many voltage sources. You can always replace it with a single voltage source in series with a resistor. And what is this VAB? This VAB is nothing but the open circuited voltage, VOC here. The open circuited voltage is the voltage across R2. What is the voltage across R2? We have already done. It's VR2 by R1 plus R2. And what is the resistance between the 2 points? Whenever you calculate the resistance, you have to kill the sources. Then the voltage source replaced by a short circuit, right? So you replace a voltage source by short circuit, then the two resistors are in parallel. So this is something I might need in future when I look at the voltage divider bias, and this is technically called the Thevenin equivalent. Of course, in Thevenin's, you might do 50 or 100 problems in the class, but I need this, right? Only this, not anything more in Thevenin's. Whenever I find a voltage divider and there is a loop, I always replace it with a single voltage source in series with resistance. This is called what equivalent? The Thevenin's equivalent, right? So this is also important. Yeah. Whenever you have a voltage V in series with R, can I replace it with a current source in parallel with some resistance? This is also very, very powerful, right? So you can have a voltage in series with resistor. Equivalent is a current source in parallel with a resistor. Then what sort of current is that? That current value is V by R. This current value is V by R. And what is V by R? It is nothing but the short circuited current, right? So you can directly take V by R in parallel with R. And what is this called? Whenever V in series with R is V by R in parallel with R, this is called the source transformation. It's called the source transformation, and this is the Norton equivalent, right? Norton equivalent. This is the Thevenin equivalent. But see how simple they are, right? You have example, you have a 5 volt in series with 1 kilo. What is the equivalent? You can replace it with a current source in parallel with a resistance. So what is 5 by 1? 5 by 1K, 5 milliampere in parallel with a 1 kilo ohm resistance. So it looks simple, right? But this is very important, right? In fact, the beauty of Thevenin is it reduces the number of loops, right? So you have number of loops here, you can cut. And for example, see, simple example I'll give you. You have a network like this. Five volt. Now, suppose you are asked to find current I, right? Now, it will be boring if you try to do it by KVL because there are 3 loops. So you have 3 equations to solve. If you do by the node method, so you have 2 nodes here, VA and VB. So again, 2 equations. Instead, what we can do is we can write like this: I equal to 5 into 2 by 1 plus 2 minus 4 into 4 by 5 plus 4 by 1 parallel with 2 plus 3 plus 4 parallel with 5. Now, how did I do that, right? Some of you would have understood it, but I'll try to explain this, right? So what's the simple thing? Instead of going for 3 equations in KVL and 2 equations in KCL, we are taking block by block, right? So suppose this one transistor circuit, this is another transistor circuit. So what do we do then? We will replace them by a single voltage in series with resistance. And this block, the block 2 here, the block 1, block 2, again we will replace by a voltage with a resistor. And then in the middle, we have this resistance of 3 ohms. Now let's go back to this simple equivalent here. So whenever you have 2 resistors with a voltage, it is equal to VR2 by R1 plus R2 and R1 parallel with R2. So let's do that. So this is going to be 5 into 2 by 1 plus 2. This is 1 parallel with 2. This is going to be 3 into 4 by 4 plus 5. And this is 4 parallel with 5. And there's a current I. Now this is basic Ohm's law. Do you know, I mean, you all know that the 1 parallel with 2 and 4 parallel with 5 and 3. These 3 resistors are in series, right? So when 3 resistors are in series, you can add them. When you add them, it becomes a single resistor. Then what is the current I? It's V1 minus V2 by R. V1 minus V2. So Thevenin's that way is very powerful. So you can cut it wherever you want, and that mesh, whatever the linear mesh is there, the equivalent is an open circuit. So you have an open circuit here, open circuit here, and finally when you join them, it becomes a single loop, right? So that's Thevenin. To me, Thevenin's is one theorem which is very powerful, very important to solve circuits, right? So bigger circuit, you can always reduce it. So this is 3, right? Here I have 3 into 4. Oh, what happened? That. It seems I should not touch anything here. Okay, so what I wanted to say is you have a you have here V1, R1, R2, R3, R4, R5. This is V2. So what is I? Tell me what is I directly? It is V1 R2 by R1 plus R2 minus V2 R4 by R4 plus R5 by R1 parallel R2 plus R3 plus R4 parallel with R5, right? So this R3 I'm not disturbing. This is R1 parallel with R2. This is R4 parallel with R5. We have V1 R2 by R1 plus R2. And this is V2 R4 by R4 plus R5. Okay. Okay. Now, how do you characterize an exponential characteristic? You can characterize a straight line with an equation y equal to mx or y equal to mx plus c. But in a first order differential equation the capacitor, the charge across the capacitor, or when it charges or discharges, it always follows an exponential path. So how do you characterize an exponential characteristic? Exponential characteristic. Because these things, they keep coming again and again. So any exponential characteristic can be characterized by two constants, a plus b. A plus b e power minus t by tau. What if my t is 0? What if my t is 0? E power 0 is 1. So it is a plus b. What if t is infinite? It is a. Then what is b? B is A plus B minus A. So it is V of 0 minus V of infinite. Is B. So an exponential characteristic can be characterized very easily if you know the initial and the final value, right? So if you know the initial and the final value, so you're much comfortable in characterizing any sort of an exponential characteristic. So you have an exponential characteristic, you should know the initial value and you should know the final value. So if you know these two things, then you can always characterize it, right? So let us substitute in this main equation. Then V of t equal to B is V0 minus V infinite e power minus t by tau plus A, V at infinite. Am I right? Or how do we characterize this? V of t can be written as V initial minus V final e power minus t by tau plus V final. So this is very, very important. So if you know that this saves time, instead of going into calculus, the rigorous method of solving using calculus, if you are gut sure that this characteristic is going to be exponential, then you can directly go and apply this formula. So you should be confident enough that the charge across the capacitor is what, when a capacitor is charging to an RC network, right, in a simple RC network, you're gut sure that the capacitor is going to charge in an exponential fashion, then you can characterize it very easily by knowing two things. One is the initial point and the other one is the final point. So if you know initial and final, by substituting in Vi and Vf, you can very comfortably characterize an exponential function. But you cannot do it with a linear form. The linear, we know it. In a linear form, suppose a constant current is flowing through a capacitor, then you cannot do this. But in a linear form, you should have y equal to mx. This is a y equal to mx plot. But what is this one? This is going to be Vi minus Vf e power minus t by tau plus Vf, right? It saves a lot of time. Say for example, a simple example. Now 1 ohm is a very small value, just for your convenience. Now I told you, if no current flows, it's as good as what circuit? An open circuit, right? This is Vc. I is phi minus Vc by 1 ohm. 1 ohm. Now, when the switch is open initially, Vc is at 0. If Vc is at 0, then what is the current I? I is phi minus 0 by 1. This is a huge current, 5 amps. So this happens, it's not such a big current, but a maximum current is going to flow through your cell phone when if your cell phone, suppose you imagine your cell phone is charging and it is charging as if it is like a first order differential equation. Then what will happen? Initially when you switch on, the current is going to be maximum, but the voltage across your cell phone is 0. Slowly your cell phone is charged to 1 volt. What happens if your cell phone is charged to 1 volt? What will happen to the current? Phi minus 1 by 1, 4 amps. So that means some less current is going to flow, right? What if the cell phone is charged to 3 volt, for example, right? So we're just having an analogy here. Don't mistake me. You can't expect 5 amps of current, but it's just an analogy that your cell phone is nothing but the capacitor, right? If it's charged to 3 volt, then phi minus 3, it is going to be 2 amps. 2 amps. What if your cell phone is fully charged? 5 amps, 5 volt. When your cell phone is fully charged, 5 volt, then phi minus 5, so the current becomes 0. Now here 2 zeros are there. One is the voltage 0 and the other one is the current 0. Now tell me, what is the behavior of the capacitor initially and what is the behavior of the capacitor in the final. Initially, this is initial. Initially, the voltage is 0. Finally, current is 0. So I told you in that voltage divider network, whenever the voltage is 0, what is the equivalent of the capacitor? Whenever the current is 0, what is the equivalent of the capacitor? The current is 0. That means the capacitor behaves as an open circuit. Initially, what is the capacitor behavior? The voltage is 0, so it behaves as if it is a short circuit. So if you know the initial and final values, then you can easily characterize the capacitor. The capacitors here, it goes from 0 to 5, 0 to 5, 0 to 5, right? Then 1 volt, 2 volt, 3 volt, 5 volt, like this. Now, how do you characterize this exponential function? It goes from 0 to 5. Is it going linearly? No, definitely not. This, when you solve the capacitor using calculus, you realize that it will simulate a linear form of first order differential equation. But we are not going into that detail. What is our aim? Our aim is we are sure that the capacitor charges in what fashion? Exponential. If it charges in exponential, then I can directly apply this formula. What is the formula? V initial minus V final e power minus t by tau plus V final. So what is the behavior of a capacitor initially? Initially, the voltage is 0. Slowly it is charging 1 volt, 2 volt, 3 volt, 4 volt, 5 volt. Finally it charged to 5. E power minus t by tau is RC, we know it, plus 5. So what is the capacitor finally? Vc of t is 5 into 1 minus e power minus t by RC. So this is an easy way of characterizing an exponential function, right? Linear form, it can be y equal to mx or it can be y equal to mx plus c. But if you are sure that there is an exponential characteristic, you need two constants a and b, and those two constants you can find from the initial and final value. So this is very, very important. Very important. You have to remember that. Very, very important. Now, what if your cell phone is already charged to V volt and now you're using the cell phone? It's not connected to the plug, now it's source free. Now you can start using it. Then, how will you characterize this? The capacitor is discharging now, discharging. V initial minus V final e power minus t by tau plus V final. So initially it is V. What happens? This 5 volt keeps on discharging. It keeps on discharging. 5 becomes 4 and 3 and 2 and finally it becomes 0 e power minus t by tau plus 0. So this is going to be V into e power minus t by tau. So the voltage was V, and now it is discharging. What if t is 0? V. What if t is infinite? It is 0. So it's going to exponentially decay, right? So these are very, very important. One is the capacitor charging in an exponential fashion. Now it is discharging in the same fashion, right? So you can see here the capacitor is charging in an exponential fashion, but now it is discharging in this fashion, the same fashion, right? Okay. Now this is an IES question. Sketch the output waveform for step input, pulse input, and square wave input. Now your input Vin is step, pulse, and square wave. So you have to sketch. This is an IES problem. I'll change the color of the pen. Now, what happens if you give a step input? The first case is step input. Step input. Let it be 5 volt or something like this, right? So you can take V volt. So what happens if you give a 5 volt to a capacitor? We have already seen this. The capacitor is going to charge in an exponential fashion. Is going to charge. See, the examiner, the IES examiner, he just wants you to sketch it, right? RC values are not given. Where RC is small, large, it doesn't matter, right? So he just wants you to have a sketch. So this is, it has charged to 5 volt. Now, according to Kirchhoff's law, what is V0? V0 is going to be V in minus VC. V in minus VC. All right, V naught is going to be V in minus VC. Then how do you sketch V naught here? V naught or VR? How do you sketch it? Now you can take the similar points here. For example, 0, right? So can you see that there is a 0 here, right? 0, there's a transition to 5. So you have to do the subtraction 2 times. So what is 0 minus 0? 0 minus 0 is 0. Zero minus 0 is 0. What is 5 minus 0? That is 5. And what is 5 minus 5? 5 minus 5 is 0. So if you take a free hand and join this, get that. So I repeat, at the transition here, at the transition you can see that there are 0 volt and 5 volt. So you have to carefully do the subtraction 2 times. 0 minus 0, 0. And 5 minus 0 is 5 minus 0 is 5 here. And then 5 minus 5 is 0 here, right? 5 minus 5 is 0. So this is exponentially increasing, this is exponentially decaying. Now it's more fun if you do with pulse and square wave. Now, how will you do the subtraction now? There are 2 points here. One is 0, the other one is 5. There's a transition. And similarly, the capacitor will exponentially charge. So how many volts? 5 volt. Now what happens suddenly? The input is removed. So there's no input now. I'll give you here T. As long as T is less than T and T is greater than T, what is the equivalent? For T less than T, you have 5 volt. For T greater than 3T, the 5 volt is removed. So now you have 2 things what we have discussed. One is here the capacitor is charging, and now the charge is going to get discharged after T greater than T. Now let's do the subtraction carefully. Subtraction. What is 0 minus 0? 0 minus 0 is 0. This is first point, 0. What is 5 minus 0? 5, because in the same transition we went to 5. What is 5 minus 0? It is 5. And what is 5 minus 5? 5 minus 5. It is 0. And what is 0 minus 5? It is minus 5. And what is 0 minus 0 is 0. So did you get all the 1, 2, 3, 4, 5 points here, right? So I repeat, what is 0 minus 0? 0. And then 5 minus 0 is 5. 5 minus 5 is 0. And 0 minus 5 is minus 5. And 0 minus 0 is 0. Now you have to take a free hand and join this. So you get something like this, right? So So here you can see that the capacitor here is what? Charging. And in this slide, the capacitor is discharging. Okay, what if RC is much greater than T? I mean, the capacitor is a little bit reluctant. It doesn't want to charge. Now, what if the capacitor has charged only till 1 volt? 1 volt. And once you remove the input, it has to discharge from 1. So this is on the condition that your RC is much greater than T. You have big R values, big C values, so it has to charge slowly, right? Now, what will be the subtraction then? What will be the subtraction? 0 minus 0 is going to be 0. 5 minus 0 is 5. 5 minus 1 is 4. 0 minus 1 is minus 1. And 0 minus 0 is 0. So if you take a free hand and join this, you get something like this. Now, what is the conclusion here? The conclusion here is, if you observe, whenever we are solving clamping circuits or whatever circuits here, can you see that this height will always remain same? Can you see? Here the transition is from 0 to 5, but here the transition is from 4 to minus 1. In the previous case, the transition is from 0 to, the transition is from 0 to minus 5. It is from 0 to minus 5, right? Here the transition is from 4 to minus 1. So the height will always remain same. So go 0 to 5 and then from 4 to minus 1. So this height will always remain same. So this is a sketch for RC much greater than T, right? And how will you draw for a square wave? How will you draw for a square wave then? How will you draw for a square wave? Let's take the same condition, RC much greater than T. And one thing you have to understand is, we are leaving the first 100 iterations, right? So you just leave, wait for a very long time till these circuits will go to a state called steady state. So I'm not drawing at 0. It's like dot. right? So we are not drawing at the 0 point, we are drawing only the steady state waveform. Suppose the steady state waveform, dot, 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 it looks something like this. Now the capacitor has to charge in both the directions. Suppose this is 1 volt and this is -1, say, for example. We just want to know the nature of the waveform. So this is not the exact waveform. We're just trying to assume that in a steady state, it is when you give from 5 to -5, it will charge as well as discharge also. In such an occasion, what will be your output? What will be your output? Now we can do the same subtraction again. You can start from 0, right? 0. First 0. 0 minus 0 is 0. 5 minus 0, 5. 5 minus 1, 5 minus 1. What is 5 minus 1? 4. Minus 5 minus 1. Minus 5 minus 1 is minus 6. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9. 9 times we are doing the subtraction, right? Okay, so where am I? I'm at minus 5 minus 1. And then what is minus 5 minus of minus 1? This is minus 5 minus 1, right? And then there is minus 5 minus of minus 1. What is this? From here we went to 5 and then 4. Where is it? 5 minus 1 is 4. Minus 5 minus 1 is minus 6. And then minus 5 minus of minus 1 is minus 4. And then this is 5 minus of minus 1 is, yeah. Now we got the, what you call the waveform, the nature of the waveform. So I'll try to, it takes few iterations until you come to this. So this is the steady state. Don't worry about the transient. From here to here, from this point to this point, it will take 100 cycles, say for example, right? So you don't have to worry. Just try to know the nature. The nature is going to be something like this, dot, dot, dot. If this node is Vx, this is going to be Vy. And what is this? These 2 points, can you tell me? If one is 6, the other one is 4. If this is minus 6, this is minus 4, right? So that means if this is Vx, this is Vy, this is minus Vx. This point, minus Vx, this is going to be minus Vy. If this is again Vx, this will be Vy. This will be minus of this Vx, and this will be minus Vy. So this is how the waveform moves after few iterations in steady state. In steady state. And all of you, can you see the height here? The height. What is 6 minus of minus 4? 6 minus of minus 4. That is 10. What is 4 minus of minus 6? 4 minus of minus 6 is 10. So you can see that this height is same as this height. And is same as this height here. Is same as this height. So the height will always remain same. When the transition happens here, this Vx minus of minus Vy or Vy minus of minus Vx, the height will always remain same. So this is a very, very important clue when you want to sketch the actual waveform. I told you this is just a rough sketch. Now I'm going to draw the exact sketch in steady state. Exact sketch in the steady state. But for that, we need 2 clues. One is because 2 unknowns are there. So when 2 unknowns are there, how many equations you need? You need 2 equations to solve when you have 2 unknowns. Now, how do you get those 2 unknowns? First clue is this waveform is called an exponentially decaying function. So what is the relationship between Vy and Vx? Vy equal to Vx into e power minus t by tau. So when it's exponentially decaying. The second clue you get is this height. This height is equal to the height of the problem, whatever the problem
చెప్పండి.
Due to some technical issue here, today's class will be suspended. Sorry, there's some technical problem. I'm not able to log in again. They say that I've just made a call. That there is some problem with the server. So I'm able to log in again. You can hear me. I'm extremely sorry for this. Right? And thank you for being patient and good night.
సరే సార్, నేను చెప్పేస్తాను, మీరు ఎగ్జిట్ అవ్వండి. Dear students, due to some technical error in our website, today's session has been cancelled. Sir is unable to re-log in, so today's schedule has been cancelled. So again, the same schedule will continue tomorrow. 2 to 4 it's DE and 5 to 9 analog. Sorry for the inconvenience. Today's class has been suspended due to some technical error. Faculty is unable to re-log in. So today's schedule has been suspended. Thank you and sorry for the inconvenience. Tomorrow the same time will start. Due to some technical error, faculty is unable to re-log in the session. So today's session has been suspended. So again, the same schedule will be continued tomorrow. Sorry for the inconvenience. Dear students, due to technical problem, today class has been cancelled because faculty is unable to read login due to our technical server has been facing some difficulties. So class has been suspended for today. Tomorrow, as usual, the same schedule will continue. Thank you. Sorry for the inconvenience.